Okay, so are you ready?
Yeah, I'm ready.
Let's get started. So today we are happy to have Gil here today, who was actually here at CITA for a while, 5 months, I heard.
Something like that, yeah.
He never wandered beyond far beyond CITA, only maybe 5 minutes. We wandered up into the wilderness today. But he started his career at Queen's University in Kingston, and then he moved on to do his PhD at the University of Chicago under official supervision of Mike Turner, but then mostly working with Karlstrom. He then went on as a Keck Fellow to the IES, Institute for Advanced Studies, and then was here for a couple of months before he became an assistant professor at McGill. Only recently he has moved away from Montreal to the United States, to the University of Illinois, Urbana-Champaign. And he has been visiting perimeter because he was missing Canada so much, just after a couple months. So we're happy to actually just catch him here today. Go ahead.
Great, thanks Dan. So it's nice to be back. So I think I last gave a talk at CITA in 2003, something like that. Yeah, so it's been a while. And
not even a Blackboard talk?
Not even a Blackboard talk, no. Anyway, it's nice to be back. So things are more or less the same, but different. So I'm going to talk I'm going to try to staple together two things. So I'm going to talk about mapping dark matter on the largest and smallest scales. So we'll see how that goes. I may only end up talking about the largest scales. So a lot of this work was done by grad students at McGill. So in particular, Yuki Amori did a huge amount of work, but Gabrielle and Ryan also chipped in. And for the second part, Yashar Hezeveh is now a Hubble Fellow at Stanford. And he's done a lot of the really interesting work that I probably won't talk about. Okay, so the first part of my talk, I'm going to talk about gravitational lensing of the CMB. So there's a lot of the people around here that work on this. But I'll go through some of that. So it's measuring large-scale structure at a redshift of about 3. So it's a very broad kernel. It's everything along the line of sight. And because it's lensing of the CMB, it's nicely complementary to galaxy lensing and also to galaxy clustering. And then the second part would be strong lensing of high redshift star-forming galaxies, which is unrelated to this mainly, but it's just the pictures are neat. So a lot of what I'm going to talk about is based on things that grew out of the South Pole Telescope project. So I know that ACT has a strong presence here, and there are arch rivals. But what is the South Pole Telescope? So it's a 10-meter telescope that's basically at the South Pole. There are 3 different sets of data that we could be talking about. So the original survey went from 2007 to 2011. And it was a temperature-only survey, but it was at 3 wavelengths, 100, 150, and 220 gigahertz, or 90, 150, 220, depending on where you define your bands. So in 2012, we swapped this out and put in a new focal plane array that was polarization sensitive. And this only had 2 frequencies, 100 and 150 gigahertz, but it was sensitive to polarization. And now, just a few months ago, we switched this out and put in the new camera, which now has 15,000 detectors, which are polarization sensitive, and again at 3 wavelengths. So so when I talk about SPT, there's actually 3 while they're all on the same instrument, they're all on the same telescope, and they're all doing broadly the same thing, there are different iterations. So just as a status update, so this is on, so we see things on the sky, but we don't yet see anything interesting on the sky. So if you're hoping to see new results from 3G, it's way too early. Okay, so you would say, why would you build this telescope? And so here's an example of just showing the power of the data. So this is a zoom in on some patch of sky. So this is 30 square degrees. So here's what it would look like with WMAP. So this is, what it does look like in WMAP. Here's the same patch of sky as observed with Planck at 143 gigahertz. Here it is with SPT pole. And so you see that as you increase the resolution here, you're starting to really see a lot more of the fine scale structure of the CMB. So all this splotchy stuff you see right here is the cosmic microwave background. And you see as with SPT, because we have a bigger telescope, we're diffraction limited, our beams are smaller, you can now really start to see this large scale structure in much more detail. And also you're starting to see individual objects. And so this map is just filtered to remove all the CMB so you could more clearly see these individual objects. And what you see is you see a bunch of white spots and dark spots. So the dark spots are massive galaxy clusters approaching 10 to the 15 solar masses, ranging at a redshift from relatively nearby out past redshift 1.5 is where we have these. These sources here are a mix. Most of them are AGN, so they're just accreting supermassive black holes glowing in the radio. But a substantial fraction of them, maybe 20% or a quarter of them, turn out to be strongly lensed, distant, dusty star-forming galaxies. And that's what the second bit of my talk would talk about. All right, so here's a summary of my talk. So the fuzzy stuff that you just saw is all weakly lensed, and here's a map of the gravitational lensing potential. And many of the dots that are strongly lensed systems, so this is an ALMA zoom in, not on in particular one of these dots, but on a dot that would look like this in our map. We get ALMA data, you zoom in, so an individual pixel of that SPT map would be about almost the size of the screen. You zoom in with ALMA, and what you see is that they're arced out into these features right here. You see an almost complete Einstein ring, and overlaid here is an HST. So this is the HST image overlaid. And so what you see is it's a strong lens. So we have a sample of maybe about 100 of these that we're slowly sifting through. Okay, so let's talk about CMB lensing. So how does CMB lensing work? Well, the idea is very simple, that there's some background screen out here, which is the last scattering surface at redshift of 1100. As we look out, we think some photon came from over here, but as it wound its way through the universe, it got kicked back and forth in such a way that it actually came from somewhere over here. So that's the challenge, is to say, well, we think it came from here, it actually came from here. If we can actually figure out exactly how much of this deflection happened, we could use that to map out this intervening potential. And so that's the idea. Why is this good to use? Why is the CMB so good for this? Well, so for one, the CMB is all at the same redshift. It's all at a redshift of 1100. We know that redshift extremely well. We know the statistics of this very well. When you're doing a cosmic shear measurement, you know that there's some galaxy there and it's been distorted in some way, but you don't really have a good handle on what the underlying statistics of the galaxy population are. You have to make some assumptions, whereas with the CMB, we're pretty sure it's a Gaussian random field where we've measured the power spectrum at high precision. It's at the highest redshift possible, at least for photons, which means it's behind all the structure in the universe. So if you want to get a complete inventory of everything in the universe, you can use CMB lensing to do this. The downside of this is that because all of the photons are coming from the same surface, you can't get any line of sight information from this measurement alone. Okay, so just to give you a sense of what we're looking for, I'm going to teach you all how to be CMB lensing people. So this is the Planck survey, and there's Polaris, is right in the center of that field. So surely you all recognize that patch of sky, right? So looking at the North Star. So this is what it looks like in the CMB, and what I've done is I'm now going to lens it with something. I'm going to simulate the lensing effect just so you can see what we're looking for, and you can see that there's a spot on this map that looks different. And actually from this image, you can actually figure out exactly what it is that you would do if you wanted to go look for this lensing. So just look at this image and say, so what do you know? Well, so if this was like a leopard in the bushes or something, you would run. There's clearly something funny about this spot, but what is it that's funny? So the spots are a different size, right? So these spots they don't look like they're the right typical size. And then on top of it out here, you see that they're sort of distorted tangentially. So what's happened is that the 2-point correlation function is different here than it is here. The correlation structures are different. That's what your eye is seeing. You're getting some characteristic spot size by looking at how coherent these spots are, and that's what your eye is doing. You're basically doing a 2-point correlation function analysis by eye. And what that tells you is that if you wanted to look for lensing, you would just look for spots where the correlations are funny. So in particular, you would look for spots that are sheared out like this, That's one form of lensing distortion, is a shear, and you're also looking for things that have been radially made bigger or smaller. So functionally what you do is you take your CMB map and you just effectively go looking for fluctuations in this clustering pattern. So not the underlying just random spots here, but instead you're looking for changes in the two-point correlation function from place to place, and you can use that to map out the potential. And so you could just do that by hand. You could say, well, let's measure the two-point function here, let's measure the two-point function here, let's measure it there. But then someone would say, okay, well, what do you do in between? So in reality, you need a bit of an algorithm to do it. And so generally when people want to write down the algorithm to do it, the language that people use is the mode coupling. So if you have some, so you take the harmonic transform, you go into Fourier space, and your two-point function is a power spectrum, and then your power spectrum changing from place to place means that you no longer have independent Fourier modes. You've coupled your modes together. So how does that work in the math? Well, the math goes, you have some unlensed sky, you do a Taylor expansion on that, and what you see is you have this term right here. Well, so you do the harmonic transform, and here you have some multiplication in harmonic space that becomes a convolution. You convolve two things together, and that means that your modes now get coupled. And the amount they get coupled is directly proportional to the lensing potential. So you go measure your mode coupling in Fourier space, and that tells you exactly what your lensing potential is. So you can use this now to reconstruct the gravitational lensing potential. So why don't I skip ahead? Oh, let's not skip ahead. Okay. Now, so what I just told you was how we do this in a CMB map, is that you do some two-point function and you're looking for mode coupling. Well, that's not the way people do it when they measure the shape of a galaxy. So let's say you wanted to measure the shape of a galaxy. So let's say you had some blob, and this thing has been sheared. Now, so when you do this with a galaxy, what you would do is you would just fit some profile in some shape. So yes, so a cosmic shear person would argue that it's much more complicated. But in general, you have some blob, you could fit some shape to it. Well, the CMB doesn't have a particular shape. So this thing right here is a Gaussian random field that has the same power spectrum as this. So this would be like a CMB version of this. And it's hard to imagine how you would just fit a shape. But if I take the harmonic transform, here's the harmonic transform, and now you see that this thing is clearly extended this way. That's the transform of this. Well, this is the transform of this. And so what does that mean? Well, that means you can actually see that this transform has some, it's a little extended in this direction, and that's because this map has been sheared in the same way that this map has been sheared. So you could equally well actually, I could use this map right here to measure the shear of this object, and I could use the square of this map to measure the shear, or I can use the square of this map to measure the shear of this. And what's interesting is actually, I could actually treat this as a Gaussian random field, use the same estimator, and I can measure the shear of this galaxy to something like, in some signal to noise regimes, I can get within a factor of about √2 for a 10 sigma object. If I just treat this blob as a Gaussian random field, I only do √2 worse in measuring the shear. So that says, so to me that says that there's some continuum between measuring the shape of an individual object and measuring the statistics of some Gaussian random field, and this power spectrum based fitting is the first step to go there, but that's a little technical. Okay, so I told you how great SPT was. And I said, look at all that great angular resolution. So this is a different version of a comparison of SPT and plunk. So I want everyone to just stare at this for a bit, because I think most people have never really looked at this before. So what am I plotting here? Well, so this is L and this is M. So these are the spherical harmonics. These are ALMs. So when you do your harmonic expansion on a sphere, you're probably used to doing quadrupoles from quantum mechanics. Well, here we're going out to us. So this goes out to L of 3000. And what this is showing is the relative weights of SPT and plunk on different parts of the sky. So high L means that we're going to small angular scales. What m is measuring, so if you remember your spherical harmonics, it's e to the im phi. So that's telling you the variations in azimuth. Now, because we're at the South Pole, the way we survey is we actually just go back and forth along lines of constant elevation. And that's so that we don't have to go through a big gradient in the atmosphere, so you just go back and forth. And because we're at the South Pole, that corresponds to a line of constant declination. So this is in equatorial coordinates. And what that leads to is this strip down here at very low m that corresponds to long wavelength fluctuations in this direction. So in this direction, if there's some long wavelength thing, we have a real hard time telling the difference between that and some drift in our electronics, or maybe atmosphere emission. And so we have a very difficult time measuring long wavelength modes that are purely in this direction. So that's low m modes. So with SPT, we don't do so well at low m. However, because we have a much bigger telescope, we do much better on small scales than Planck does. So this is small scales, this is large scales. However, on the very largest scales, what happens is we again start to lose stuff in the atmosphere. And so on very large scales, you're much better having a satellite that's out in space, doesn't look through the atmosphere. On small scales is where these things like SPT and ACT are much more effective. So what you're seeing here is you're seeing sort of this region here is where SPT is really good. And here is where Planck is really good. And when you see it plotted this way, you can sort of guess at what we've done, which is we took the maps and we spliced them together. That we basically took Planck data and filled in these modes. And out here, we just left the SPT mode. So you take these two things and you stitch them together. And what that gives you is it gives you a map that over our entire 2,500 square degree area has well understood noise properties, and that is a reasonably good map of the sky. Okay, so, and this is work that a lot of this was done by Ryan Chown. He's a graduating master's student. He's going to McMaster in the fall.
And the top part is the same.
So this top thing is actually from the fact that we're only looking at 2,500 square degrees. And so if you imagine, so L equals M corresponds to the spherical harmonics that go pole to pole. And if you have a survey that only is covering a certain area, then you're going to lose some of that. Some of those modes just can't be supported. So this is from the survey mask. So this is from 2,500 square degrees. And as you move our survey up and down, what you find is that this line goes up and down. Okay, so we take our SPT map and we turn it into a Dlensing map. So I should have. Okay.
Can I just, so that's LM.
Yep.
If I want to think about complete 2D Fourier, then the M is a bit, I mean, I guess it's the M of the phi L plus a hat.
Yeah, so L is square root of kx squared plus ky squared.
In terms of qx, qy.
Q.
Well, or, sorry, q.
K's, right, yeah. Yeah, so L is the radius, and M is it kx or it's L squared minus kx squared, I think. I think this is what M is. It's either this or it's kx squared.
I'm not quite sure that's true. So you're saying that M is basically...
And there's a geometric factor. M is one of these, so let me think about.
I mean, it's like the L is like the magnitude of K, and
yeah.
M is
the
angular variable transform.
M is going around.
And
that's
so
right. That's right.
This is a big deal.
It's
I'm trying
KX.
to make this into a rectangular plot.
Yeah, I think it's KX.
Simply, it must.
Yeah, so M maps directly into one of your Ks, and then L is the radius.
Right.
But you have to be in the right coordinate system for for the SPT observing to map into this stripe, you need to be in equatorial coordinates. Because if you rotate your pole, you mix all your M's together. So if you're in galactic coordinates, this strip would get spread all through here.
the SPT crossing isn't the equivalent of the ACT crossing.
We have no crossing.
Exactly.
So luckily we are not, fortunately we're not cross-linked. That's what makes this work so well.
Oh, it works better? Not
It works better to be not cross-linked.
Oh.
Yeah.
Well, that may show the problem with looking into space. That cross-linking is good, not bad.
Well, we're cross-linked with by using Planck. So we fill in with Planck. So the stuff that we lose, we fill in with Planck. Yeah, so if we were not at the South Pole, if we were in Chile, then if we go back and forth like this, in equatorial coordinates we're moving along some tilted line. And that means that we wouldn't be just losing low M modes, it'd be some complicated track in the space. So, but by finding the right coordinates, it makes it a very easy thing to stitch together.
I still don't see it, but we just try and find the right space
Yeah.
to show the difference between ACT and SPT in terms of the equivalent of your dark blue line.
Yeah, I agree. So I think in ACT, I don't know what it would look like. I don't know whether it's a line. Anyway, we could find it. It's easy to write down. It's also even easier to Monte Carlo it. You just, do these things and then take the transform. Okay. So what do I want to? Okay. I actually didn't show the map. All right. So here is our lensing power spectrum. So we make our lensing map, and we take the power spectrum. And what you see here are so in the background boxes is what you do with Planck on the full sky. And so that's the best lensing measurement to date is the Planck full sky map. And so the full sky is a lot of sky. 2,500 square degrees sounds like a lot, but there are 40,000 square degrees in the sky. So it's less than 10% is our patch. And then what we have here is we have two different sets of band powers which are ours. One is SPT only. So the SPT only ones are in blue. And then SPT plus Planck only in our patch you see here in purple. And so what you see is that on large scales, all this work of stitching things together didn't change anything. And why is that? Well, it's because on very large scales, if you look at this map, while it's true that there's this yellow area down here and down here, there's lots of modes in here that SPT has measured well. And so adding just a few more modes down here actually didn't help that much for the case of measuring these large scale things, because what we're looking for is we're looking for mode coupling. So if you're looking for mode coupling of some separation of L, you say, how many pairs do I have of this separation? And then how many new pairs have I gained by adding Planck? Well, I haven't added that many new pairs of small separation. And so for small separation mode coupling, SPT alone is almost as good as Planck in our patch, but we don't have as much sky as Planck, so therefore our constraints, our error bars are bigger. However, where you see the difference is when you start looking for larger scale mode couplings. If you're looking for mode coupling separated by some fraction of this ruler, well, it actually helps quite a lot to be able to push down here, because you see, it used to be I had this pair and this pair and this pair. Well, now I have this pair and this pair and this pair and this pair and this pair. So by just adding a few more modes in here, I can greatly increase the number of large separation pairs. And so that's what you see here, that with SPT only, you see out here at large separations, which corresponds to high L, small scales, you see our error bars from SPT alone start to blow up, but the combined map, you see still has very small error bars even as you go out to L of almost 3,000. And so this is why we did this. So the motivation for this was for doing things like cross correlations with the dark energy survey or with any other astronomical survey you could imagine if you wanted to be actually able to compare your CMB lensing map with a galaxy map or a cosmic shear map. Smaller scales, the more modes you have, the smaller scales you can get to, the smaller error bars, the better that comparison is going to be. Yep.
Maybe it's just a trick of the plot, but it looks like it's a pretty sharp transition between the SPT and SPT plus Planck error bars being the same, and there being.
You mean right here?
Yeah. Do you expect it to be like that?
Well, so one reason for that is that when we do SPT only, we often put a hard edge right here in the SPT only map, because at L below 1,000, it looks like it's fine. There's no obvious problems with the data, but that's where our noise does start to roll up. So generally we just cut it off here when we do the SPT only, and you can see that there just aren't pairs past, say 2000. And so we cut it off here for foreground considerations. So, so that is a real jump. Okay, and then there are null tests that we pass. Okay, so that's our power spectrum, but you can see that for the most part out here, that Planck full sky measurement is still beating our best. And for cosmological parameter estimation, it turns out most of the cosmological power is coming sort of in this area right here. And that's just from the, if you just look at the noise statistics. All right, so I'm going to skip this stuff.
So one aspect of this is that you can do power spectrum and all that. Can you make an AL estimate on these?
An AL, this actually is AL.
Oh, okay.
So we don't have the SPT only plot on here, I don't think. Yeah, so here's AL. And so there's different ways of doing, so let's just look at the dashed on this plot. So the Planck lensing on its own, so Planck lensing tells you that you would get some number kind of like this. So the amount of lensing you see is roughly what you would expect. The SPT A lens is consistent with 1, but slightly lower, but it's not high. So there's sort of this long-running discrepancy in the Planck data that if you look at the Planck power spectrum, so that's probably easiest to see in this solid line right here. Well, so the Planck power spectrum, so remember we're doing mode coupling, right? So lensing does mode coupling, which means you have some power spectrum. And if adjacent modes are coupled, it smears out the peaks a little bit. So it just brings the troughs up and brings the peaks down. And Planck can measure that. And using just the shape of the power spectrum, so if you just do a fit to the Planck data, you see sort of this 2 sigma hint that the amount of peak smearing is a little bit high. It sees maybe 25% more peak smoothing than you would expect given how much structure we think there is in the universe. And you see that 1's pretty far down in the tail. There's a little bit of support here. It's not ruled out, but it's uncomfortable. And so this propagates through a lot of the fits for Planck that it just says there's too much lensing going on, a little bit too much lensing. How do you get too much lensing? Well, you have too much structure in the universe. So if there's a little bit more structure in the universe than what you expect, that propagates all the way through. And in fact, where it really shows up is when you look at constraints on neutrino mass. Because neutrinos are if neutrinos have mass, you're basically taking some amount of the dark matter and putting it in some free streaming component, and that means that there's less clustering on galaxy scales. Instead, Planck is actually measuring more clustering through more lensing, which means there's really no room in the Planck data on its own for massive neutrinos. But that's just from the smearing of the peaks. If instead you go into the Planck data and you actually look for which modes are coupled and use that to reconstruct the lensing potential, you find that there's exactly as much lensing as you expect in just the Planck data. And then you look in the SPT data, and this curve looks similar as you would expect for SPT only. I don't have that curve here. But you see with SPT in our patch, we also see, if anything, less lensing, not more lensing. So there's something weird going on. It's unresolved at this point, but it's something to keep an eye on. As these surveys come in, are we all going to converge on exactly as much lensing as we think there should be? So ACT should be able to say something about the peak smoothing. So soon ACT will be able to say whether the peaks really are smeared. But it's this weird state of affairs where it looks like the peaks have been smoothed a little bit, but apparently not in exactly the way you would expect lensing to do it. So who knows? Something to keep an eye on.
So sorry, and it gets lower just because you have those smaller error bars at high and low?
No, this is all the way through. So most of this is dominated by, most of this fit is actually dominated by this. So you could see these are the Planck boxes right here. And you can see that when you look right through here, the Planck data, you know, if you sort of do a chi by eye, these tend to fall just a little bit on the low side. So the Planck data on its own, if anything, goes a little bit low, and you see that we're the same way. We're just a little bit on the low side. So out here, the statistical weight is almost 0, just because the error bars are too big. Most of the statistical weight is coming from down here. So it's all coming from sort of L below about 500. And it's really not clear what's going on. So that's sort of the one anomaly that is still floating. Well, not the one, but it is an anomaly that's kind of floating around that that's something to keep an eye on. Okay. So, wow, I can't believe I never showed there. So there's our map. So one thing, and so this is a map we're using the SBT-SZ survey. So this was the 2500 temperature only survey. This is from SPT Pole. This is a zoom in on this patch right here. Right, 100 square degrees right here. So this has signal noise that's something like 5 times better than this signal noise. But what you could imagine doing is, you know, this is a real map of large-scale structure in the universe. This is kappa, so this is the dimensionless surface density. So to put it in reasonable units, you'd have to get some estimate for what redshift you're looking at. But so these are fluctuations of a few percent on, and you see that these are degree scale fluctuations. But this should be an honest-to-God overdensity in the universe. This should be an honest-to-God underdensity. And so one thing you could do is you could actually just take like a Herschel map. And so this is a 500 micron Herschel map. This is the CMB lensing map, the one that I just showed you, that SPT pole map. And on this side, the grayscale and the contours are both overlaid. So this contour goes with this image. And that's just exactly this image right here. Oh, where do we go? That's this image right here, flipped around probably. And now here I've taken these contours and I've just laid them on top of a 500 micron map. So this is just a straight Herschel map. Just Herschel 500 microns, smoothed in the same way as this lensing map, and I've just overlaid the contours. And what do you see? You see that actually some of these spots really do line up. You see that some of these dark, you know, this is a hole in the CMB lensing map, corresponds to a void in the galaxy in the 500 micron map. And you see there's some hot spots here that kind of line up. You see some spots that don't really line up. But that's okay. It's okay that they don't all line up because this is just a map of all the 500 micron emission, which is not going to exactly trace where all the mass is along the line of sight because we know that star formation doesn't exactly trace the mass distribution. And on top of that, this is a lensing weight, which means we're more sensitive to stuff exactly halfway along the line of sight than at either end. So it's okay that it doesn't match up perfectly, but what's nice is that it does match up to some extent. And if you calculate what the expected cross correlation should be between CMB lensing and something like a 500 micron map, you should find that they should be correlated at the level of, the power should be correlated at something like 40 or 50%. And as you look at that, that's roughly what you're seeing, is that some fraction of these really do line up. So we're going to come back to this in a second. Now, what you can also do with this, so this is with 500 microns, so you know, there's lots of stuff you can do. You can do a cross spectrum and calculate the exact mapping between where the 500 micron flux is and where the mass is. But you can also do this with galaxies. So we've done this with galaxies with the dark energy survey. You can do it with quasars. So we did this with a WISE catalog of quasars, as well as with the Planck map. You can do this with SDSS quasars. We've done it with cosmic shear. So you can take some other way of weighing the mass distribution, and some of the galaxies are being sheared by the same structure that is relatively nearby that's also lensing the CMB. So you can use all these things and you can do sort of a monster consistency test. You can stitch them all together and say, are all these different probes tracing the same density field? And when you do that, you can then get at questions like, how does light trace dark matter? How does the dark matter structure evolve with time? And so that's one of the things we're doing. Okay. Now, another thing you can do with this 500 micron map, and eventually we'll do this with the CMB map, is delensing. So I told you about lensing. Well, what's delensing? Well, to understand delensing, you have to understand a little bit about polarization maps. So this is a Stokes U map. Does everyone remember their Stokes parameters? So Stokes Q is telling you the relative intensity fluctuations in, say, the horizontal direction versus the vertical direction for polarization, and Stokes U is tipped over at 45 degrees. So Stokes U is telling you whether there's a preference for electric fields coming in this direction versus this direction. So that's Stokes U, and so this is a CMB map. And remember, the CMB is a Gaussian random field, right? Now, so you look at this map, and I don't know about you, but I see lots of diagonal stripes. And you might think that that's a problem with our experiment, but you just see that in general, this structure you tend to see stuff, ripples that are going more at 45 degrees than things that are this way. There's some characteristic boxiness to this, that it doesn't quite look right. It's not a completely random field. And why is it not a completely random field? Well, it's because the CMB, while it is a Gaussian random field, the polarization fluctuations are sourced in a funny way. They're sourced mainly by scattering of the scalar fluctuations. You have some gravitational potential, things are flowing, and so it's the motions of the fluid at recombination that are sourcing these polarization fluctuations. And what that says is that the directions that things change are what are sourcing the polarization. So the orientation of the polarization vectors are correlated with the directions in which things change. So if you then were to do a Stokes Q map, what you're going to find is that when the electric field vector is either at this way or this way, that means that that's going to be correlated with structure that's changing in this direction or this direction. And these are what are known as E-modes. So when we talk about E-modes and B-modes, we're talking about Stokes Q maps, Stokes U map that tend to vary on lines of 45 degrees. Stokes Q would be things that are varying mainly this way, and those are E-modes. But you could imagine polarization. You could imagine making a Stokes U map that doesn't have any boxiness. It could just do some random field. It doesn't need to be that way. And so those correspond to B-modes. Now what's nice about B-modes is that you don't expect to see them in the CMB unless there are gravitational waves careening around at the surface of last scattering, or possibly vector modes would also do it. But if you can measure these B-modes, then you're actually measuring the gravitational waves coming from inflation. And so here is the expected B-mode contribution. So these are not those boxing, these are the Stokes U map would be, the fluctuations would be straight up and down or this way. Those would be B-modes. Well, what do you expect those to be? Well, that depends on how many gravitational waves you have. So the tensor to scalar ratio, there's R of 0.4, 0.1, 0.01, 10 to the minus 2, 10 to the minus 3. And what you see is there's a reionization bump and then they fall off. This line right here is what you get from gravitational lensing of that Stokes U map. So imagine that I take some gravitational lens and I put it down here and it does some crazy distortion of this pattern. Well, there's no reason that a gravitational lens that I put down is going to respect any symmetry of this background map, which means I'm going to generate B-modes from this initial E-mode map just from gravitational lensing. And basically any low redshift effect that goes mucking around with your CMB map should cause B-modes. So gravitational lensing is thought to be the biggest effect that's going to be generating these B-modes. So there's the spectrum. What I've overlaid right here is a white noise power spectrum with an amplitude of 5 micro-K in an arc-minute pixel. So that's a good number to just, if you're going to walk around and talk about B-modes, you should remember this number of 5 micro-K arc-minute. It says that if you want to image lensing B-modes, you want to make a map of the B-modes coming from lensing, you need to have a sensitivity in a 1 arc-minute pixel of at least 5 micro-K. And if you don't get to this polarization sensitivity, then you're only going to have a statistical map of your B-modes, which is fine. You can do lots of stuff with that. But if you really want to image them, you got to get down to this depth right here. So this is, so with SPT pole, we're not quite to this level. With SPT 3G, we should go a factor of maybe 2 or so below this level. The far future is CMBS4, where people are talking about going, maybe even 10 times below this level. It's still up in the air how far you'll go. However, what you see is that if you wanted to measure these inflationary Bmodes, these lensing Bmodes are in the way. That if you have this noise at 5 micro-K arc minute, you're going to have a very difficult time getting down to this sensitivity. And so you might think that that's a floor, but I just showed you that you can make these maps of the gravitational lensing potential. So if you have a map of the gravitational lensing potential and you have your Stokes U map, you could actually use that map to undo all of the deflections that have been put in. And once you have that, you could then get a more pristine view of last scattering. So that goes by the name of Dlensing, and it's people have, sort of in the same way that people are coming around to the idea of we are going to have to do some kind of carbon capture if we want to get the, control global warming. People have sort of accepted that we're going to need to do Dlensing if we're going to actually go hunting for gravitational Bmodes down here. So it's a very new thing. I think the first Dlensing has only happened in the past few months, 4 months maybe. But the idea is very simple, is that you just have your measured E-modes, and there's lots of ways you can measure your E-modes. You can measure them at different frequencies. In principle, you can use your temperature map to guess what your E-modes look like. So you have your measured E-modes, and then you need some estimate of phi. And there's different ways you can get your phi. You can actually get it from your CMB map. So I showed you that we reconstruct the CMB lensing. You could use that map. But I also showed you that we're something like half correlated with the cosmic infrared background. So what's nice about this map is that the cosmic infrared background map, while it's only about half correlated, it's extremely high signal noise. There's effectively, for our purposes, there's no noise in that 500 micron map. So for our purposes, we're using this right now. Eventually we'll go on to using our CMB maps. But basically, you know what your phi is. You have your measured map. You just take your phi and you just unlens, undo the deflections, move everything back to where it should have been if it was lensed like this. So that's one way to do delensing. The other way is you can go forward, you take your phi, you take your measured E-modes, and you say, well, I'm just going to lens these ones again, and that'll give me a B-mode map. And that tells me exactly which B-modes should be there, and then I just go looking for these on the sky. So this is how SPT first detected B-modes a few years ago, is that we made this predicted B map and then cross-correlated with our data and said, oh, look, we see these B-modes. That's great. We detected B-modes. But now, instead of saying, oh, great, we detected them, we're actually going to just subtract them from our data. So with SPT, we did this. So we start with our E-modes. We use the phi map from the CIB, generate some B-modes. And then subtract that from our data. And so this was a really nice analysis by these guys, so Manzotti, Story, and Kimmy Wu. So the three of them actually, it was genuinely a team project. I don't know if anyone here uses Slack, but SPT uses Slack a lot for collaboration, and so I was on that chat and I was just watching, and this, every day you would just see the paper build. It was actually quite nice to see them work. So they did this. And then after a huge amount of work, they delensed the SPT B-modes. And so in the end, after all this work, it doesn't look like very much. However, so here is the lensing B-mode power spectrum that is predicted from theory. Here is the SPT measurement of our B-mode power spectrum before delensing. And then they went through and they generated this map, subtracted it from our data, and then made the power spectrum again, and what you see is that indeed the B-mode power has dropped by about 20%.
So what does it mean to do a subtraction since there's statistical errors? So is it, all that's presumably folded in. I guess what I'm trying to ask is, can one more or less do one operation that doesn't involve a product being a D-length map?
Well, you don't have to look at the D-lens map, that's true.
But you know what I mean?
Yeah, no, you could write down an expression.
Is that you're going to make this D-lens
Yeah.
map, and then you're going to do measurements on
Yeah.
it. But if fact, that whole process is folding in complex errors
Yep.
associated with the delensing and all
Yep.
of the uncertainties in that. And that would then have to be encoded in the theory of errors in
Yep.
the delensed map. And it seems that there is sort of a almost top-down way to go as opposed to trying to, I mean, it's
Yeah.
not unlike the issue of, well, you know this very well, that do you really want to try and map back dark matter and galaxy distributions?
The reconstructions for BAO.
Fundamental initial condition modes, or should you try and get the results from the theory of how complex it is, taking into account all these correlations that you're getting the extra information on?
Well, I mean, so you can't do it all just at the power spectrum, just as pure power spectra, because then you would lose all the phase information.
Exactly. So
And
you
the
have to-
phase information, yeah, and so that all has to be in there. But it's true that you could just write this down as you start with some power spectrum and we're going to subtract off all of the things that we know are there. So what's interesting is that a couple days before this paper came out, Julian Caron and Anthony Lewis and Challenor did a similar version with the Planck data, where they delensed the Planck data. So with the Planck data, it's actually much noisier. And there they had exactly the problem that you are talking about, which is that this delensing process introduces noise. This is not a perfect map. This has some noise in it and some imperfect correlation. This has some noise in it. So this has some noise. And when you subtract something noisy, you're adding power to your map. And so you can calculate exactly how much power you've added. And so for our analysis, we actually added only maybe a few % of power for us, because our maps are, our E-modes, this is this map is probably hundreds of sigma, whereas the Planck E-mode map is signal noise of order 1 in the map. So we don't have a huge amount of noise, so this thing for us was not very noisy. On the Planck version, they did this process, and if you actually look at what they did, the before and after picture looks identical. They say, we started with our power spectrum, we did all these manipulations on it, and look, we get exactly the same power spectrum out as what we started with. And you might think that doesn't do anything, but they, as you point out, well, they know that they added a lot of noise. They added some amount of noise to this process of delensing. So because delensing added noise, if you did something that added noise and ended up with the same power as what you started with, you must have removed some of the intrinsic power.
But they're delensing E and T, or no? Where are they delensing?
They delensed everything. They did E, T, and B. It's amazing that you wouldn't think they could do B, given that they don't even measure B.
Right.
So this was what's amazing, is that they don't even measure the B-mode power spectrum, but what they can measure is that when they do the delensing operation, it doesn't add power, which means they must have removed some power. And they don't know which power they removed, but if you delensed and your power went down, then you probably removed your lensing B-modes. So it's an interesting it's an amazing analysis. It's really quite impressive. So for us, it's much easier because we know that we didn't add very much noise, and so we saw it go down. We went, oh, okay, we're done. So we removed about 20% of the power, is roughly what we removed. So just to orient you, so for CMBS4, what people are talking about is delensing by something like a factor of 10. So not 20% of the power, but they're talking about if you want to really build an experiment and go after these gravitational waves on this level, you need to get rid of 90% of the power. So 20% versus 90, we're on our way. We're not there yet, but we're on our way. And so this whole field of delensing has really only started recently. So it's going to get better as the data gets better.
Just going back to this, but there is multiple scale information, which if you're doing the sort of top-down analysis, you would be able to come up with numbers that would take all of that simultaneously into account. I mean, so the statement of dropping that line down by that factor of 10, you could do that inhomogeneously and
Yes.
still get effectively the same result, more or less, not going to be perfect, but.
inhomogeneously.
So the situation here is you're saying you gotta just de-lens everything with, you know, this fantastic accuracy.
Yeah.
But you could miss some scales, have holes.
Oh,
all
that's
that
true.
Stuff, and you would still get much the same result.
Yeah, you could. I mean,
But that, in these sort of de-lensed pictures, without showing the fluctuations, the
Yeah.
errors, would be rather difficult to get across. I mean, it's sort of like looking at
Yeah.
complex feeder filtering, where you can have, you know, all sorts of noisy patterns that are not a nice uniform noise.
yeah, no, that's exactly right. And in fact, we are not equally delensing all of these spots. We are better at delensing some spots than others, and the reason for that is actually this E-mode map. This is our E-mode map. But remember I showed you that we had that missing stripe in M in our temperature map. We're missing that same stripe in M in our polarization maps, which means we don't have all of the E-modes. So because we don't have all of the E-modes, we don't get all of the B-modes that have been generated. And because that has some scale dependence, that means that our B-mode map is better on some scales than others. And so, you know, that gets folded in. And so here it's been reduced into this, you know, 1D plot versus L, but you could do this mode by mode. You know, there would be some transfer function where you could say how well we remove all these. And that would be an interesting analysis. Okay, so that's where it's going. So I'm just going to show you a pretty picture of one of these dots. So it's not exactly this dot, and in fact it wasn't from the SPT survey. So I'm just going to give a little teaser of what the second half of my talk was, and then I'll stop for questions. So here are ALMA images of 5 of not these dots in particular, but things that are statistically similar to these dots. So these are ALMA images on top of HST images, and what you see is these are all strong gravitational lenses. So, you know, some of them look like happy faces. Now, so you might think, do we really need more gravitational lenses? Because I don't know about you guys, but I've seen hundreds of these images of gravitational lenses, or maybe I've seen the same one 100 times. But so, you know, it's nice to have more. You know, it's nice to, these are amazing systems. We could actually weigh these galaxies. So there's lots of stuff you can do with that. These are zoomed in images of sort of ranging from redshift 2 to redshift almost 7, some of these. I don't think this one is, but one of our sources is almost at a redshift of 7. This lensing magnification lets you zoom in and actually see detailed structure in these sources, so you can actually get glimpses of star-forming galaxies. These background objects are intrinsically interesting objects. They're even after the flux boosting for lensing is accounted for, the star formation rates are hundreds of solar masses per year. These are incredibly vigorously star-forming galaxies. They're very interesting to a lot of people, but not me. So what I like about them is what we're using them for is as looking for dark matter substructure. And so I got started on this through SPT because we found all these sources, but Herschel also has a bunch of these. ACT has a bunch, Plunk has a few. And so there is this population of strongly lensed galaxies, and what I like about them is that you can use them to gravitationally map out the fluctuations in the intervening gravitational potential. So in particular, what we think a galaxy should look like if you had dark matter eyes would be something like this, where you have sort of a central blob, and it should have all of these companions. Now, what we empirically see is that in our galaxy, we don't see nearly this many, we don't see nearly as many lumps in the outer halo, and people argue about whether that's actually a problem or not. So it goes by the name of the missing satellite problem, but people, you know, it could be that it's just solved by baryonic physics, but regardless, what we think is going on is that any gravitational lens source should have some population of small subhalos. So now imagine that you have some image of a background source, and let's say it started as some nice like monochromatic red, green, blue, and it goes through this potential. What you see is it gets distorted. And in particular though, all this blue ends up here, and you get multiple images of the blue, and you get multiple images of the green, and multiple images of the red. And some of these images are going to fall close to a little dark matter clump. And when that happens, what should happen is that this image should get ever so slightly distorted by this gravitational clump, by the gravitational potential of this clump right here. And so with sufficiently high resolution ALMA images, what you can do is you can actually do a joint reconstruction and say, okay, well, what does the source look like intrinsically? What does the gravitational potential look like? And are there any small perturbing clumps that only affect one set of images? So what's nice about this clump is that it'll muck around with this blue flux right here. It'll barely change the red and the green, but it won't at all affect these blue clumps, which means you can use these blue clumps to figure out what the source looks like. And then the distortion here would then be able to tell you that there's actually some perturber right there. So that's what we did. So we did that on this data. So we reconstructed the source. So this is what the source looked like. Here's the Dlensing caustic. And so it's a clumpy, dusty star-forming galaxy, a redshift 4 or something like that. So it's incredibly vigorously forming stars, so you don't expect it to just look like a nice little simple clump. It's a mess. So you see that it's a mess. But in this case, it being a mess is a feature. And why is that? Well, because if this was all just one big blob, you're not going to get small, fine-scale features in that gravitational lensing map. It's all just going to get blobby and sheared out. So the fine-scale features here actually help us find smaller structure in the lensing potential. So we went through, and in the end, what we found is we found a clump. And so there's not really an easy way to show this other than to say, so here's a fit to this image. So here's the image we fit to. And what you can say is you can say, well, can we match this flux using a smooth model? So here's the best fitting.
Go back to that for a second.
To what?
Is that really CO 8 to 7 transition? Not that, I think it was the next one. That's really carbon monoxide from the rotation state 8 to 7.
Yeah.
We're all into CO here, and that's just, we aren't thinking about 8 to 7, are we? That's fantastic.
Yeah, so with all these things, you have the redshift, so you pick up, what was that?
I said it's amazing how impressive that emission in CO is for such an obscure high-level line transition.
Yeah, but
it's all defined by what Alma gets to look at, right?
Yeah, and it's also, there's a huge amount of dust, right? This is forming stars at hundreds of solar masses per year. So it's an incredibly vigorously star-forming galaxy, so there's probably like, hot spots all over the place, so you get these high excitations. But what's nice about this is you also see this is color-coded by velocity, so you see there is a lot of velocity structure. So that's why I had that image color-coded red, green, blue, because you do this using a line like this, and this is the equivalent of your red, green, blue, is all the different velocity structures. So it's a neat thing, but it is hard work. And in the end, what you end up with is there's the best fitting smooth model, and here are the residuals. And what you see is there's a residual in here, and this cross is here because this is where we think there's a clump of substructure in the lens. And if you instead use a smooth model, you see that a lot of the substructure goes away. There's a little bit left. But what you can really see is that if you compare the smooth model versus, oh wait, this is band 7. Here's the perturb model, good. So this is band 6, band 7. This is just two different wavelengths. What you see is that the difference between these two shows a lot of substructure right here. And that's because what's happened is there's a little clump of material right here, and what it's done is it's shifted this flux out a little bit. And that's what you're seeing right there. So we detected this at about roughly, so you can see that we can constrain the mass of whatever this little perturber is at the level of about 10%. So it's a 10 to the 9 solar mass subhalo, which is unfortunately not quite the super interesting range. That's basically just a little bit less massive than the SMC. So the small Magellanic Cloud. The interesting range, the more interesting range for subhalos is to get down to more like 10 to the 8. But you can see that even with this image, we're already getting sensitivity at the level of 10 to the 8 as our 1 sigma on this particular observation, which was not tailored for these purposes. What was that? Oh. Yeah. Well, we definitely don't constrain it that well. It's the detection was around 10 sigma. So what I meant to say is that we measured the mass to be 10 to the 9 solar masses with a 10% error bar. So perhaps but isn't that what that is? No, that should be plus or minus 1, right? Well, it's I don't know. You know, so it's a 10 to the 9 solar mass clump, and it has about a 10% error bar. So that's what I meant to say. Sorry. So in principle, we actually have something like 100 SPT sources. We're currently running this on 3. So right now, the analysis takes a very long time. It's computationally intensive because the amount of data here is, it's ALMA data. It's not it's only a few minutes of ALMA data, but ALMA has a lot of telescopes, there's a lot of correlations. So it's a computationally challenging project, and we're working on ways to speed it up. Okay, so I will stop right here and just leave these up and take questions. Thanks.
All right, so we went a little bit over time.
Yeah,
so,
sorry about that.
At least time for one question. So is that clear? Actually, I had one question. So why is the SPT as Z-lensing result after the polarization result?
Well, so there was an SPT-SZ lensing result that Alex Van Engelen did, who you all know.
Right.
That was based on 20% of the survey. And then it was basically, it effectively came down to the person that was working on the SPT-SZ lensing basically fairly abruptly left the field.
And now it's at Google. Is that right?
Not at Google, no.
I thought it was
It's not Duncan, no. So he's working somewhere else, and so it's sort of, we had to basically shift gears and then start. So, it in the end comes down to personnel, and
Right.
eventually we just had to get the right personnel working on it, and Yuki Amori is the right personnel,
Right. Okay.
and now it works.
Okay. And so then
But it actually, well,
is applicable to the polarization results directly, or
not directly, but it is. So one of the reasons, so there actually is a technical reason why it took longer, which is that this analysis was done all in curved sky, using ALMs and not flat sky. And the reason we wanted to do that was because, so for SPT pole, it's the field, so the first field was 100 square degrees, and then we grew that to be 500 square degrees. But even that you could all do in flat sky. You don't need to use curved sky to do 500 square degrees, whereas once you're doing 2,500, it's 11 hours. And so what's a miracle is that flat sky actually is sort of okay on something that goes from over there to over there. You would think that you shouldn't be able to just project that onto a flat map and not have some problems. However, once you're doing that, to me, it made a lot more sense to just do everything as one monolithic chunk and do it all in curved sky and just have everything in heel picks and make it just one big thing. And then you can uniformly go from Planck maps to SPT maps to whatever maps you want to do. And whereas with the SPT pole stuff, it was all flat sky, and also Duncan Hansen was doing it.
Okay.
And Duncan Hansen works at about 10 times the rate of normal humans.
Okay. Good. All right. Well, any other questions